Thank you, Pedro, for the flattering introduction. Of course, it's my pleasure and great honor to be able to address the peer-to-peer community this morning. Thanks for showing up. And let me see, it's not perfect because I can't see my laptop. So I'm going to have to look a little bit at the slides sometimes, and I'll hope you'll forgive me. Okay, so I also hope you're not offended by my slightly provocative title. But I think it is, after all this tremendous amount of work that's been done over more than a decade now on peer-to-peer systems, it's perhaps fair to ask this kind of question and look back. And, game changer or red herring, you can probably guess that my answer is going to be a little bit of both. So I'll start with a list of caveats. First of all, I have not actively worked in peer-to-peer systems for a number of years now. And I also have to confess that I have not been able to keep up with all the most recent work in recent years in peer-to-peer systems. So forgive me up front if I'm missing some important pieces of work, or perhaps I'm leaving out or misrepresenting some of the more recent pieces of work. But there's been so much work, right? Even if I had tried to keep up, it would probably be impossible for me to do justice to all the great work that's been done in that area. And finally, of course, I no doubt my views are biased by my own work in the past on structured overlays and DHTs. In any case, I take full responsibility for any nonsense that I might say, but in as much as you might find any of these thoughts useful, I should credit these many collaborators, former students and current students who have contributed to these ideas and who I've had the great pleasure to being able to work with over the years. And in particular, I would like to mention Ann Drostern, of course, who did with me the original pastry work. Started actually IPTPS with me, and also contributed to some of these ideas in the first part of the talk that I'll talk about today. Okay, so in way of outline, I'll give a very, very brief overview. Then I'll focus on a few things that I consider to be P2P technology challenges, and that continue to be technology challenges, and that are important to understand if one thinks about what P2P technology is useful for and what it is not. And then in the second part of the talk, I'll actually talk a little bit about some more recent work that we and others have been doing that was originally inspired by peer-to-peer systems, and I think has some interesting applications potentially for peer-to-peer systems, and then I'll conclude. So as you all know, starting around the year 2000, actually a little bit earlier in 1999, this huge flurry of activity started around peer-to-peer systems, sparked by some of the really innovative ideas in systems like Napster, FreeNet and SETI at home, leading to a lot of activity both on the open source community deploying innovative new systems and starting up the research community looking at this problem. And like many similar technologies that get this sort of massive early attention, the whole phenomenon has experienced what some people have termed the roller coaster of the hype cycle, where there's an initial implosion of visibility and activity, inevitably leading to some inflated expectations about what the technology will be able to do and how it's going to change the world, followed by a rather rapid downswing where people get disillusioned because they realize progress is not as quick or as significant as initially anticipated. The challenges turn out to be harder than initially anticipated. And then finally followed by a modest rebound or a more modest rebound, and finally reaching the so-called plateau of productivity, which presumably we've reached now. And this is a good time to look back at what is important and what is not. Very briefly, you all know this, among the most popular P2P applications today is of course content distribution. Initially file sharing networks, now BitTorrent is the big player. Increasingly, streaming media distribution is relying on peer-to-peer networks. We all use Skype, tremendous impact, no doubt. And finally, peer-to-peer technology has unquestionably also had an impact on data centers, even though these systems are not peer-to-peer systems in the strict sense, right? The technology has clearly had an impact in the form of key value stores and similar types of technology. And finally, volunteer computing continues to be, actually from the start and still continues to be a major significant application. Now, you may notice that peer-to-peer storage is not on this list, and this is kind of ironic because a lot of the early deployed systems and most of the academic research in the early part of the last decade was focused on peer-to-peer storage systems. Okay? And so it's interesting that actually this side of the thing hasn't panned out, and I think, you know, I'll at least submit that this has something to do with these challenges that turned out to be much harder than originally anticipated. This is a very, very, very brief, you know, summarization of what I think are some of the key peer-to-peer technologies. Obviously, there is much more, but I think these are the ones that really stand out. A lot of work on unstructured overlays, how to use epidemic techniques to maintain these overlays, how to distribute content, how to find content. Then the other side of the coin, structured overlays based on key-based routing, which have led to DHTs and a whole bunch of techniques to coordinate activities, find content, and so forth in this world. And finally, I think swarming, you know, pioneered by BitTorrent, of course, is another one of those real cornerstones of that technology. And again, this is not to insult any other work that's been done. I know there's much more, but these are sort of the things that I think stand out, arguably. Okay, so let me leave it at that. You all are familiar with the technology. I don't, you know, there's little I can tell you about it. But let's talk a little bit about the challenges. Here's a list of things that, ironically, were considered by many of us, particularly in the academic community, initially as sort of engineering details, whose importance or significance fades compared to things like, you know, what is the right overlay structure, and you know, should we have unstructured or structured overlays, and so forth. And these things, I think, turned out to be actually much more important. And some of them turned out to be really hard, and in fact, some of them are still very much open challenges that in fact limit the applicability of peer-to-peer technology. So let's go down that list. So I'll start with some things that I think we know a lot about and arguably have mostly solved, and then getting into things that I think are very much still open problems. So physical network efficiency deals with, you know, how can we make the overlay actually make efficient use of the underlying physical network, typically the internet in a peer-to-peer network. And that has to do with you know, making sure that neighbors in the overlay who coordinate and communicate frequently and closely do not, in fact, are not paired among nodes that are distant in the underlying physical network, thereby leading to low bandwidth, high latency routes, and, you know, resulting in inefficient communication and poor performance. So this boils down to choosing neighbors not only in terms of, you know, with the goal of satisfying a certain graph structure, but also to achieve efficiency with respect to the underlay. And I think there's been a lot of work that originally was a little bit underestimated, but it's been largely successful, and we know now how to build these systems with routing stretch, you know, below a factor of 2 compared to simple IP communication in the internet. And we also know how to efficiently form spanning trees of one sort or another among groups that allow them to communicate efficiently. So this has been largely a success, and even though, you know, anyone building a new system has to pay close attention to this, I think it's largely a problem that we have a handle on. There's also the aspect, of course, of how to make internet traffic play well with the business model of ISPs, but that's something that Pablo has talked about yesterday, so I'm not going to go into that. The second one, and again, I think this is something where there's been a lot of good work and we have a good handle on, is achieving robustness to dynamic membership and dynamic events in the underlay, in the internet, right? So this boils down to making sure that you can sustain a high rate of node joins and departures, which requires efficient topology repair, and I think it's critical to have mechanisms to aggregate activity related to concurrent events that are going on, concurrent you know, join and departure events. Similarly, underlay partitions, you know, some large-scale failures in the internet that either cause a set of nodes to completely be partitioned or appear to, you know, like a massive failure of participating peers have to be dealt with, and this is a tricky problem. You know, one aspect of it is having sufficient overlay connectivity to not lose connectivity in the overlay when in fact the underlying partition is not complete, and in the case that the underlying partition is in fact complete, having active reintegration techniques and dealing with the split universe problem, you know, where your world splits into 2 or more parts where each part of the overlays thinks that it's the only one surviving and all the others have failed. Sorry. And another one, of course, is having to deal with routing anomalies and things like NATs and firewalls in the internet, which lead to things like A can talk to C, A can talk to B, but B cannot talk to C. And unless you take care of this, of course, you're going to have convergence problems and stability problems. And people had to learn how to deal with these issues over time. But again, by and large, I think this is something that we have a handle on. Now, a challenge that's still, I think, considerably more tricky is how to provide incentives to cooperate. Clearly, a system that depends on cooperative research contributions needs to have robust incentives. Relying on altruism alone really means building on a weak foundation. There's been a lot of interesting work on incentives mechanism, some of them very simple and effective, like tit for tat and BitTorrent. But of course, the problem gets harder if you cannot identify peers that want the same thing at the same time as in BitTorrent and can help each other get what they want. Right? It's much harder if you're trying to balance, for instance, storage contributions to data insertion in a peer-to-peer storage system. Other general techniques that people have looked at are reputation systems, where you're trying to assess the past performance or past behavior or degree of contribution of peers based on subjective statements by other users or other peers users. Or equivalently, accountability techniques, which is what I'll talk about in the second half of this talk, which try to reason objectively about the performance or the compliance of certain peers. And of course, you can use both as an indirect way to provide incentives, because both lead to essentially tarnish the reputation or record of a node that doesn't contribute fairly. An even harder problem, perhaps among the hardest of all, is controlling membership. And the problem is that Sybil attacks are really a fundamental problem affecting peer-to-peer systems that have loosely controlled membership. And of course, the problem is not limited to peer-to-peer. It also affects many of the web services, social networks, and so forth. And the problem really is that an individual that can control multiple entities can do a number of really nasty things. It can shed whitewash bad reputations, rendering effectively reputation, even accountability systems, useless. It can manipulate its own reputational history via fake transactions among its Sybils. It can manipulate protocols based on voting. It can circumvent per user limits that you might impose to defend against denial of service attacks and things like that. And nastily, it can undermine the fault model that you usually have underlying replication, okay? Because there's always ultimately an assumption that the peers in the replication group do not fail in a correlated manner. But if it happens that all of them are controlled by the same person, of course, that's very much not the case. Simple defenses, there's been a lot of work on this, a lot of really interesting work. It's still a very, very hard problem. General idea, as you know, is to tie link account creation to some limited constrained resource, so you can rely on trusted authorities and somehow tie it to a passport, a phone number, or a credit card. But unfortunately, this conflicts with privacy, which is a serious problem. You can require upfront work or a monetary payment as a way of at least reducing the rate at which a single individual can create multiple identities. But this is fundamentally vulnerable to resource-rich attackers, either a deep pocket attacker who has lots of money to dole out, or someone with access to a botnet or rented cloud facilities. And to balance the concerns of defending against those rich attackers against the desire to not make the barrier to entry too expensive in terms of money or resource is a fundamental problem, I think, that's hard to get right. And then there's a whole bunch of work, as you know, that leverages social links, where the idea is that a real individual is limited in the number of actual social links it can form, particularly if those social links actually require reciprocation, so they're not unilateral, they require bilateral consent, and they have actual meaning. People are not just gratuitously agreeing to forming social links. But the upshot is that all of them tend to increase the barrier to user adoption, and this is a really hard problem, because most of these systems desperately want to attract attention and want to have more users. Malicious peers is another problem that I think is a challenge that's been mostly unanswered. There's a number of threats, a number of nasty things that a malicious participating peer can do. On the side of confidentiality, of course, it can leak private information or disclose the partners in an anonymity network. And on the side of integrity, it can sort of prevent messages from reaching the desired correct peer, either by dropping or corrupting messages, or by biasing routing tables, which is also a very nasty attack. Right? You basically selectively propagate information about other peers in order to make sure that people preferentially refer to other malicious peers that are collaborating with the attacker. And you can, of course, also impersonate the responsible peer, either by choosing particular identifier values in a structured overlay network, or by using many identifiers, thereby probabilistically being likely to be in a given position in the overlay. Now, crypto helps here to the extent that many of these, not quite all, but many of these can be reduced to DOS attacks through appropriate crypto mechanisms. That still leaves DOS as a problem, though, because that's not to be underestimated, particularly in a system that depends on cooperation. There's also been a lot of work on this. Secure routing is one example. It's fairly complicated. You need to secure the node identifier assignment, basically presuming a solution for the Sybil attack, right? Which we know already is hard. It requires a membership protocol that prevents this kind of routing table biasing attacks. Requires a secure routing primitive that prevents impersonating a particular node. And then when all of that is said and done, right, which has quite an expense, you can tolerate up to about 25% malicious nodes, at least in this particular work. There's also been competing approaches that rely on BFT replication, basically forming logical nodes consisting of several physical nodes. But they have similar problems with complexity, with fault assumptions, and overall expense. So I think this is largely an open challenge. Keeping persistent state. And this is now highly relevant, of course, to the question, why don't we have popular P2P applications that actually have persistent storage? And I would submit it has to do with these challenges. So there's, on the one hand, the problem that the required bandwidth to just maintain the required level of replication for persistent storage is, of course, proportional to the degree of membership churn. Right? Whenever there's membership churn, you need to potentially re-replicate. The volume of the data, obviously, because that increases the bandwidth for re-replicating data, and obviously the degree of replication. And as we know, right, you can pick two of those, but all three is really difficult. The other, I think, problem that's not to be underestimated is that for any reasonable degree of replication in a very large system, right, there's always some replica group that will violate its fault bound, meaning it has too many faulty nodes in the replica group, meaning that those particular objects are not safe. And then finally, this problem that's well known, that if you have shrinking membership, it could lead to a very quick collapse, because the amount of available storage is no longer sufficient to actually hold all the data that was committed into the persistent storage. Again, there's a lot of interesting work, but I think it's very difficult to get it all right, along the lines of using multiple levels of replication. Having typically the approach is you have a few replicas that you re-replicate very eagerly, okay, immediately when a node departs or fails for availability. But you have slightly more replicas, additional replicas for persistence, that you replicate on larger time scales. In other words, you want to take advantage of the fact that a node that departs might come back the next day with its disk storage intact, still having the replicas available, right? So no need to panic immediately. But that even is not really sufficient for major disasters, where in fact a large part of your peers might be vulnerable to a worm attack affecting a particular operating system that's very popular, right? Wiping out its disks. So to defend against that, you need an additional mechanism that you know, typically uses erasure coding to create a very high degree of partial replication in an efficient manner. But to maintain those replicas is potentially very expensive, so you can only do it on even longer time scales, you know, typically weeks or months. And finally, this whole thing has to be combined with some sort of an incentives and a robust incentives mechanism that makes sure you know, you don't collapse as your membership turns down. And I think this has to, for instance, go along the lines of making sure that the persistence guarantee you offer for data is not absolute, but it's tied to appropriate resource contributions. So, you know, your data is only safe as long as you are, in fact, contributing enough storage and often enough. And the final point that I'd like to get in is management. This is something that I think is perhaps to some extent least understood, particularly in the academic community. But it's tricky, right? On the one hand, you can look at the benefits and say, well, peer-to-peer systems are self-organizing and they have automated fault recovery. They do that because they are decentralized. And also, peers look after their own hardware, which is, you know, if you combine the two, you have very, very low-cost day-to-day operation. And it explains the fact that, you know, we've had examples of a single graduate student operating a system that has millions of users. That's really quite impressive, right? I mean, there's not many other technologies that would allow you to do that. And it also means there's a very low barrier to deployment, right? You have an idea, you write some software, you put it out there. With very little upfront investment, you can get something deployed and tried out. On the other hand, some of those same things actually introduce new challenges. The fact that you have all this automatic configuration and fault recovery can easily mask underlying problems. And anyone who's operated a peer-to-peer system actually with a few users has experienced this. If you're not careful and you don't have appropriate monitoring infrastructure, you may actually miss problems until they're too late, right? They've actually aggregated to an extent where the system is becoming unstable and very hard to recover. And the fact that, you know, peers look after their own hardware also comes with a price, namely you have no homogeneity and it's very difficult to have quality control because everybody installs, you know, their software slightly differently. They run different operating systems, different configurations, different network providers. It's a shaky ground to stand on. And so it's been very difficult to actually ensure system stability and quality of service in large-scale systems of that type that depend exclusively on peer contributed resources, right? Things obviously get much easier if you have some dedicated infrastructure that you can rely on. Okay, so how do actual peer-to-peer designers deal with that? Well, I would submit that you know, if you look at the deployed peer-to-peer systems, they mostly avoid these more difficult challenges. Okay? In data centers, it's obvious there's infrastructure, you have centralized control, you're eliminating all these problems related to peer contributions, to heterogeneity, lack of trust, in combination with some infrastructure. So Akamai Net Session is a recent commercial system where, you know, a traditionally infrastructure-based CDN provider is now including peer-to-peer elements, but in such a way that most of the coordination, control, and trust continues to rest on the dedicated infrastructure, and that, of course, helps tremendously. And I would submit, you know, where you see peer-to-peer, it's typically in applications that have weak consistency requirements and soft state. So no permanent data, at least not at a high volume. So if you take a step back, right, about the strengths of weaknesses, and again, I may be stating the obvious here, I think the real strength of peer-to-peer technology comes from this independence of dedicated infrastructure and centralized control. Okay? It means you can deploy something with very low upfront investment. It grows organically. It's very robust to shifts in the workload. But if you look at the weaknesses of peer-to-peer systems, they're actually rooted in exactly the same properties. Right? The absence of dedicated infrastructure and centralized control gets you in trouble with you know, what do you do when you can't maintain your quality of service based on the currently available resources, or because of the heterogeneity of those resources, or because you lack centralized control. And of course, these weaknesses do lead to technical challenges that we're still struggling with and grappling with, and also business and legal problems. And I think one just has to, without being negative here, one has to be aware of these limitations and find the right application spot where this technology can really shine. So what is it good for then? I would submit, and again, you may disagree, and I hope there will be some discussion about this. There's no doubt it's a great, and it's in fact a unique technology platform for services that focus on free speech, privacy, anonymity, and censorship. It's unique there in the sense that there's no alternative. Okay? If you want a system that is robust to powerful attackers, censorship, and coercion, you need to avoid dedicated centralized infrastructure and in the peer-to-peer space. But I think it's also a very interesting technology that you can view as a low-cost deployment vector for experimental innovative services, right? That you can deploy with very little upfront investment without a business model even, right? And you see how it catches on. If it becomes successful in a commercial sense, you can then always turn it into a hybrid system by adding centralized infrastructure component, thereby increasing quality of service, increasing other properties that you find hard to fulfill in a purely decentralized manner, or I should say in a purely cooperative manner, because that's the really important aspect, not the decentralization. But I think we should not make any mistake. Utility cloud computing is a competitor here. Okay? It also allows you to potentially deploy a service with very little upfront investment because you pay by actual usage. And so often it comes down to anticipated resource costs. If your service has fundamentally high resource costs relative to the number of users, then you're driven more in the direction of peer-to-peer because you don't have to pay for the actual use, whereas a cloud utility model would charge you for that. Okay, so at this point I'd like to shift gear a little bit and actually talk about, as I said earlier, about some more recent work we've done after I stopped being very active in peer-to-peer systems. But this work was actually very much inspired originally by peer-to-peer systems and some of those problems that I just talked about. Again, faults and misbehavior are something that it's not necessarily common, but you have to reckon with in peer-to-peer systems. And the reasons are it's large scale, right? So there are many hardware and software faults. There are multiple administrative domains, which means trust is decentralized, control is decentralized. Peers don't necessarily have interests that are perfectly aligned, okay? And you have a lack of transparency because they don't necessarily disclose all of what they're doing and all of what they're after. And you have this dependence on cooperation, which makes you vulnerable to abuse or even just selfishness. So if you think about this list here, it's not all that different from society at large. Okay? You deal with any society or large organization of people, you have the same problems. And if you look at how human societies or human organizations deal with this, it's interestingly mostly based on accountability. Okay? So the idea that you let people you trust people up front, you let them do what they're supposed to be doing, but you have mechanisms in place to verify what they did. And if there is a problem, there's a way to find out that there is a problem, there's a way to find out who's responsible for it, and there's typically a way of actually proving who is the faulty party to a third party, such as a judge at a court of law. So if you look at banks, and I'm talking here about conventional banks, and I'm not, by the way, talking about investment banking, there's a system of commitment implemented by signed receipts, paper receipts. You go to the bank, you deposit some money. You don't do that anymore today, but in the past we did, and we could in principle still do it. You get a signed receipt proving that you actually gave them the money. There's also a tamper-evident record implemented as, in the form of double-entry bookkeeping, which makes sure that one party cannot unilaterally change the books in such a way that there wouldn't be an obvious discrepancy, okay, which alerts someone to a potential fault. And there's a system of inspections, right, called audits, by which either the bank internally or the tax authority or law enforcement can come and inspect the books to see what happened, if something illegal was done, and if so, who's responsible for that. So in the offline world, of course, this is all done manually, by and large. So the question is accountability useful? The departure point for this work was, the question, is accountability useful in distributed systems, and particularly also in peer-to-peer systems, and is it practical? So in a technical sense, accountability, I would submit, should mean the following, namely the combination of some mechanism of maintaining a tamper-evident record, right? A record that records what happens in a system in such a way that if any one party were to try to distort or revise that record, it would be evident. Okay? Plus a fault detection mechanism, and in the case of an information system, I would submit that such a mechanism has to be automated. It cannot be manual because, given the verbosity of transaction logs in a real peer-to-peer system or any distributed system, it would be impractical for people to routinely check them manually. And moreover, you want this to be reliable because otherwise you have too many false positives and you're back to the problem that you have to, go through all these logs manually to figure out is there a real problem or not. Obviously, I'm not trying to say here that accountability is something that would supersede fault tolerance. It doesn't, right? In particular, if you look at systems in which faults have severe and irrecoverable consequences, like launching a missile, dispensing cash, right? You can't, accountability is of limited usefulness. You need fault tolerance, and of course we have a lot of literature on that. But the answer is yes, I would submit for systems that provide best effort services, and a large class of peer-to-peer applications does just that for other reasons. Okay? And also for systems that depend on user cooperation, because there you're particularly concerned with knowing when someone is not doing what they're expected to do, namely, follow the protocol and contribute resources to the extent they can. So accountability in this sense would enable you to reliably detect and localize faults and malicious peers, and thereby indirectly provide incentives for people to cooperate and avoid misbehavior in the first place, because they know I'm going to be found out and there's going to be some repercussions. Maybe I'll be kicked out of the system. And so it actually helps, just as in human society, accountability helps build trust and reputation in a reliable way. Here's a quote by Butler Lamson from a more than a decade-old paper, which is sort of interesting in this context. I'll just let you briefly glance over it without commenting it. Okay, so let's look for a few minutes at what is actually a realistic goal for accountability in a practical system. So let me sort of loosely or informally define a fault as an instance of a node that deviates from the expected behavior as defined by either a specification, if you have one, or more practically, as defined by a piece of software that you know implements the protocol that you expect your peers to run, and everybody agrees that's the authoritative copy, right? It may have bugs in it, but by and large, the community agrees that this is the correct behavior, right? It's not been doctored by someone to do freeloading or censorship or something else. And then our goal relative to these faults, the goal is to automatically detect when such faults happen, identify the faulty nodes, and convince potentially others that in fact a fault has occurred or has not occurred, which is the mirror image. You also are interested in being able to prove to others that in fact you did comply. The sort of starting question would be, is it possible to build a system with the following guarantee? Whenever a node is faulty in any way, faulty being defined as in this way, the system generates a proof of misbehavior against that node. And as you might guess, because I'm making making such a fuss of this, this is actually not practically possible for a number of reasons. First of all, if you think about faults of the type where a single bit has been flipped in the internal memory of a particular peer, detecting that fault immediately and generating a proof of misbehavior would require you to have some kind of an online trusted probe at each node that looks into the memory and constantly checks, has a bit flipped. And if so, generates some proof, which means you need a probe that's constantly looking at the memory, and this probe has to be trusted. Well, that's not practical. So instead, what we do here is to focus on observable faults, where observable faults are faults that actually affect a correct peer in the system. So for instance, if this node that has a bit flip eventually, as a result of this bit flip, sends a message X to a correct node C, such that the correct node without that bit flip would not have sent this message X, then this becomes an observable fault. And that's what we focus on. And the nice thing, of course, is this, we can do this without requiring additional trusted components. You just rely on the observations of the correct nodes that you already have in the system. So the second question is, can we always get a proof? And unfortunately, the answer to that is also no. And the problem are these kinds of situations where, a node says, I sent X, and the intended receiver says, I never received X. So from the perspective of a correct node that's an observer in the system, there are three possible explanations, right? It's possible that A is actually lying. It never sent X. It's possible that B refuses to acknowledge X, even though it has received the message. So B is lying. Or it's possible that neither is lying, and the network has lost or delayed the message, because after all, we are in an asynchronous model. So this means we cannot really fundamentally get a proof of misbehavior in all cases. And so instead what we do is we settle for something we call here verifiable evidence, which is either a proof of misbehavior in situations where you can get it, and typically that's the case when you have a commission fault, meaning someone sends a message that is clearly wrong, okay? Or a challenge that a faulty node cannot answer. And the challenge comes into play when you have situations where someone should have done something, but it hasn't happened yet, and you're not quite sure what the reason is, okay? So in this particular case here, in this example, the message X itself would be the challenge, okay? Because a faulty node that doesn't want to acknowledge X for some reason, because, for instance, it might ask it to do something it doesn't want to do, would not be able to acknowledge X. Okay? Whereas a correct node that just didn't receive the message because the network was temporarily unavailable would simply be able to acknowledge X and thereby exonerate itself, answer the challenge. Okay? So what do we do while such a challenged node has not yet responded to the challenge? We put it into a so-called suspected state. Right? We don't know if it's wrong or if it's faulty or not, but we put it in a state where, for instance, the other correct nodes in the system might refuse to communicate with it and basically cooperate with it until it has answered to that challenge. Okay, so there's a few other things that I should have to, would have to go through to really make this precise and cover all the details, but let me cut it short at this point and just say, if you take into account these observations we just made, you can revise the guarantee that you want to provide for accountability in a peer-to-peer system to the following, right? Whenever a fault is observed by a correct node, you see that we have the limitation now to observable faults. The system eventually generates verifiable evidence. You see the restriction to verifiable evidence, which could be proof of misbehavior or a challenge. We also inserted eventually, you can guess that's because of the asynchronous network, against a faulty node. You also notice that there is a faulty node. I didn't say the faulty node. And the reason for that is, I didn't go into the details of that, but if you have multiple conspiring faulty nodes, because we cannot observe communication among the faulty nodes, right, because it's not visible to a correct node, we cannot in the end say which of those faulty nodes committed the incorrect state transition. However, and this is interesting and important, in practice we can still tell that the conglomeration as such, right, the set of conspiring nodes has in fact committed a faulty transaction of faulty state transition if the fault is observable by a correct node. So one of those faulty nodes will be flagged. And of course, I wouldn't tell you this if, in fact, it didn't turn out that we can make this practical. So there's a system that we and co-authors had designed a couple of years back. Actually, it's been 5 years, called peer review, which is the basis for a number of techniques in that space. You can think of it as a library that does two things. It provides this tamper-evident logging of the set of interactions in a distributed system, say the set of messages exchanged among the peers, and it detects faults based on this tamper-evident record using a particular mechanism that's based on state-machine replay. It's based on a number of assumptions, of course, as any realistic system. It assumes that nodes can be modeled as deterministic state machines. That's, as you know, in practice, not such a big assumption. Any sort of state machine replication does the same. It assumes that there's a reference implementation of the state machine that is considered to be the correct one. Okay? That's also a reasonable assumption because anyone who participates in a peer-to-peer system has an idea of which is the correct software. It's usually the one that they themselves run, right?
and also nodes have unique signing keys. A PKI as such is not required, but you have to rely on everyone having unique signing keys. Let me quickly tell you a little bit about this, how this works, this system. From 10,000 feet, imagine we have a set of nodes, say in a peer-to-peer system. I'm showing them here as a ring, but actually the topology doesn't matter. So the first thing that happens is that all the inputs and outputs that a node sends and receives are recorded in a local log. So each node maintains a local log of all the messages it sends and receives, and a few other inputs that, for instance, it gets from its applications. So in particular, whenever a message sends a message M, it logs this message in its own log, sends the message, and then the receiving message logs it also in its own local log. Okay? Then there is a concept of witnesses. So among the other peers, there is a dedicated set of witnesses whose job it is to periodically audit A and determine whether it's been misbehaving or not. And it does this by fetching the log, periodically of node A, applying a test to it, such that if A in fact has misbehaved, these witnesses are guaranteed to determine that deviation, assuming that they are themselves correct. Okay? And if they are, they will generate some evidence that can then be distributed to other interested parties. What's an interested party? Well, typically other nodes that interact with A, okay? Such that these interested nodes can, based on this evidence, for themselves decide whether or not A has committed a fault without trusting the witnesses. Okay? And this is important because you don't want to have a complex trust chain. Let me tell you a few more things about how this works in practice. So first of all, of course, you have to prevent tampering. People should not be able to modify their own local logs in a way that it looks as if they had, in fact, complied when, in fact, they misbehaved. So this is done with a number of mechanisms. First of all messages are signed. So when a node A sends a message, it's supposed to sign it. When a node B acknowledges that message, it's also supposed to sign it cryptographically. Secondly, the local logs that all nodes are maintaining are organized as a hash chain, okay? Such that the most recent entry includes a hash of the previous entry, thereby committing the entire chain. And furthermore, whenever a node signs a message, whether it's a message or an acknowledgement, it includes in that signature the top-level hash of its current log, thereby effectively committing to its entire history. Okay? So you can easily see that if a node later on tried to change its log to hide, sweep some dirt under the rug, it would cause an inconsistency because it would not be able to produce later on a log that is consistent with some of the hashes that it has included in its own past messages. Okay? And this makes these changes in the log evident. So there's another thing we need to do to prevent omissions. So for instance, suppose I send a message, but I simply do not include that message in my log. How do I find that out? It's done the following way. You already know that periodically A's witnesses here fetch the log from A and inspect it, okay, for the purposes of fault detection. When they do that, they also watch out for authenticators, basically signed messages that node A has received from other nodes. So for instance, suppose that node A has, during the audit period, received messages from node B. Okay? A's witnesses will collect those authenticators and, as a side effect of its own checking, send those authenticators in bulk to B's witnesses. So by this mechanism, B's witnesses will eventually find out about all messages that B has in fact signed or acknowledged. Okay? So if B were to not include any messages it actually signed and sent in its own log, it would cause an inconsistency that B's witnesses would detect. Okay, and finally, we need to do something about load forking. You can imagine a clever node might say, okay, let me at some point fork my log, such that, suppose in one view of the world, I acknowledged a command to create an object X, okay, and I said, okay. But then when another node asks me for X, it says read X, I say, no, not found. Okay? And I do that by basically branching my history here, presenting to different nodes, two different views of the world, which of course cannot be consistent because, it's not possible that this object has been created and not deleted, and then it doesn't exist. So the way this is handled is that the witnesses, as part of their log checking, also check whether there is a linear log segment connecting any two hash values. So if a node forked its log, eventually one of its witnesses would try to obtain a linear chain between H4 prime and H3, say, right, which doesn't exist. The node cannot produce that chain, and therefore it's going to be caught. Okay, so I've, of course, still omitted some details here. It wouldn't be possible to go into all the details in the available time, but I think you probably get an idea, and in fact, suffice it to say that I tell you, you can prove that based on these mechanisms, that this log is in fact tamper evident, meaning given a set of logs that you collect from your peers, you can tell deterministically and reliably whether that log is in fact consistent with the actual set of messages exchanged between those peers over a period of time. Okay? And if not, if it's not consistent, you can pinpoint a particular node, one or more nodes, who have obviously doctored with their logs. So at this point, we know that we have an accurate reflection of the actual messages exchanged between a set of peers. Okay? But we still don't know whether, in fact, misbehavior occurred, whether someone made a protocol state transition that they shouldn't have. And for that, there's the fault detector. And this particular fault detector makes, you can imagine many different fault detectors. This particular one uses state machine replay, which has this beautiful advantage that it's completely general, meaning you don't have to understand at all what the protocol is supposed to do. And all you need is just a correct implementation. Okay? You don't need a specification. So what you do is, once the witnesses have checked the logs for consistency, what they do is they take the log, they instantiate their own copy of the state machine. Namely, they take the software that they know to be true or they believe to be the correct one. Okay? And then they feed the inputs from that log into that state machine and see if it produces the identical outputs. And again, one can show that if, in fact, the original peer that you're auditing has performed the state transition they were not supposed to perform, there will be an inconsistency here, and you know that their software behaves differently. So if you put all this together, you have a system with two principal guarantees. One of them says that observable faults will be detected as long as a node has at least one correct witness. One correct witness is sufficient. And secondly, a good node cannot be accused. Interestingly, even if all of its witnesses are faulty. And the reason is that it's impossible to actually produce a proof of misbehavior against such a node, and it can answer any challenge that you might pose it. And there is, of course, some formal treatment about this. We've applied this technique in a number of different contexts, for an NFS server, so not a peer-to-peer system at all, but just to see how it performs with small latency-sensitive types of requests. We've applied it to peer-to-peer overlay networks and to a peer-to-peer email system that we built a number of years ago. The beauty of it is, of course, that with one mechanism, it handles a wide variety of misbehaviors. In fact, any type of misbehavior that causes, that has as an underlying feature, a change in the software or a change in the configuration will be reliably detected by this. And of course, because you have this mechanism in place, you have a general incentives mechanism, because people know if they misbehave, they misconfigure, or they change the software, they will be caught. Okay, of course, this all has a cost, which it's difficult to state in an application-independent manner, but across the applications that we have looked at, there's principally three costs. There's log storage, and that can range between 10 and 100 gigabytes per month on typical peer-to-peer applications that we looked at. But keep in mind, you don't have to keep these logs forever, right? You just keep them long enough for your auditors to have a chance to inspect them. So that's in practice not really a terribly expensive aspect. More expensive are the message signatures, right? You need to fundamentally sign all the messages, and if you're using something like RSA, a 1024, which is no longer sufficiently strong for most applications today. It adds about 1.5 milliseconds RTT, which is not a big deal in a wide area network, but it is non-trivial in a local area network. Of course, there are different crypto systems that are more efficient, and that helps. CPU overhead is also, is a potential concern. In our experience, it's not that serious because you have lots of cores and it's embarrassingly parallel. The other principal cost is that you have to transfer these logs and authenticators to your witnesses, right? So there's a cost that depends on the number of witnesses. In fact, for technical reasons, it's if you want perfect reliability, it's quadratic in the number of witnesses. What helps here is that typically the number of witnesses you need is relatively small. It just needs to be large enough that with high probability you believe that at least one of them is correct. And the other advantage is that unlike in state machine replication, right, we can defer the checking to periods of low load. Like if you have a diurnal load pattern, you can easily do that during the night. And so in our experience in most peer-to-peer systems, there's two effects that really help you. You have diurnal load patterns, and the typical node is not 100% utilized during normal operation, which means that the auditing proceeds much, much faster than the original execution. Right? Your witnesses basically do the checking during the night or during periods of low load in compressed time. Okay, so to summarize that part of the talk, and in fact I'm nearing the end in any case, so this technique is useful in that it detects faults and identifies the faulty node and produces evidence, okay, that you can use to convince other peers that don't necessarily trust you whether or not a particular party has committed a fault. We believe it's practical for an interesting set of applications, including peer-to-peer applications, and it has this interesting aspect that in peer-to-peer it addresses both incentives and malicious peers, which are two fundamentally difficult challenges. It does not itself do anything about Sybil attacks, unfortunately. Okay, you still need somehow trusted identifiers for this to work, because otherwise someone could just misbehave, get caught by the accountability mechanism, but simply continue to act under a different ID. That brings me to the end. In conclusion, I would say peer-to-peer has definitely changed content distribution and a number of related applications in a very fundamental way. So tremendous impact. Okay? It's also influenced data centers through aspects or parts of its technology in a very fundamental way. Great success, no doubt. Actual peer-to-peer systems that rely on cooperative resource sharing, you see them deployed today in environments where I would argue the toughest challenges don't come to bear. Right? And that, again, that's perfectly fine. It's just important to understand those limitations. So, mostly they don't have persistent data. They're not sensitive to Sybil attacks. They typically don't pay attention to malicious nodes, either because it's not a problem or because there's not a sufficient number of them today, or because the management is actually not fully decentralized. We talked about how peer-to-peer strengths sort of are also their weaknesses, and that seems pretty fundamental. And then in terms of the uses, I think P2P is a great vector for low-cost deployment of innovative services, and I think that's continued to be the case. It will continue to be the case. And obviously, it's a unique platform for free speech, anti-censorship, and privacy. So I think there's a lot of stuff that the peer-to-peer community can be proud of. There's also some challenges that may or may not be amendable to robust solutions in the near future, but that doesn't detract from its value. And with that, I hope you enjoyed some of these thoughts. And thank you very much, and I'm looking forward to your questions. Yeah, that's fine.
Okay. So thank you for this great talk. I totally agree with the first half of your talk. I'm still not totally convinced with the second part. If accountability really helps to improve a lot. The main problem are denial of service attacks. So, and with this system, with accountability, you increase the complexity, and probably it's also difficult to prevent denial of service attacks in the system itself. And even if you detect that a node is malicious, how do you exclude these nodes from the systems and prevent them from doing further denial of service attacks? So the question is, isn't it better to try to design a P2P system or protocol which deals with misbehaving nodes and by introducing redundancy, for example, and actually have a simpler system with the same overhead as this approach?
I think your concern is perfectly reasonable. Let me try to answer it by saying a little bit about the history of this work, actually. We around 2005 or 2004, I had a number of students build a peer-to-peer email system, which, we published it eventually, but it didn't get a lot of attention. Partly, and we knew this because, clearly email is not a killer peer-to-peer application. The reason we actually did it because we wanted to see if we could build a system that actually deals with persistent state and provides a service that the users really, really cared about, right? Because most people would not want their emails to get lost or they to be leaked to attackers and so forth. So we thought it was an interesting challenge to ourselves to see whether we can build a peer-to-peer system that provides this sort of high stakes service, but still one that hasn't have consistency requirements that would just be really, really hard to fulfill with peer-to-peer. Because by and large, right, the multi-writer issues are minimal in a peer-to-peer system. It's mainly per person mailboxes and so forth. So we built the system and we tried to do all the right things, right? We put all the right crypto in, which was complicated but feasible. Then we embarked on trying to put the secure routing work in it, right? Just to prevent attacks where someone would just shut down the system with a few malicious nodes that strategically messed up the overlay. And by the way, this attack is very easy to mount. And that added tremendous complexity to the thing. And we hadn't actually really addressed incentives issue in any meaningful way. And this was actually the point of departure where I said, this is not going to work, right? The system is already tremendously complicated. There are still known problems that we have with incentives and with various types of DDoS attacks. And we have no confidence that there aren't, a gazillion other attacks that we're not even aware of. And this was actually the point of departure, and this led to this thing, which is on the surface, non-trivially complex mechanism, granted. But I think once you get your head around it, it's actually pretty straightforward. And once you do it, you actually have a safety net, right? Because it has a very generally statable guarantees. So it captures, in fact, any kind of misbehavior that depends on misconfiguration or changing the software. And that it sort of indirectly solves the incentive problem. So I would, on that point, argue that yes, it has non-trivial complexity, it has non-trivial cost, but it is in fact a very general mechanism that gets you a whole bunch of stuff out of the way. And we were actually able to take all this secure routing stuff out of the system, right? There's like 40 or 50,000 lines of codes that they were just pushed out of the repository. We were no longer needed. But nevertheless, right, I'm not saying that your concern is not valid, right? It's something that needs to be looked at for a particular system closely.
Yeah, thank you very much, Peter, for your talk. And I have a question, to the second part of the talk. We have to do with the persistence of the identifiers, because your system, peer review, is putting a lot of effort on identifying the malicious actions from participants, so logging and creating evidences. But the thing is that I just said it at the end of the presentation that a malicious node can rejoin the system with a new identity. So the effort of the whole system trying to identify and create evidences of that may be useless at the end. So my question is, just talk about the design decision of putting so much effort on identifying malicious participants instead of the maybe the good ones, when you are, there are more probabilities that they are not going to rejoin the system with a new identity and they will behave as expected. So about that. Thank you.
My answer is a little bit similar to the previous question. Right? You're right. So accountability still depends on reasonably strong identifiers. It doesn't do anything per se about Sybil attacks, which is a huge bummer. Right? I'd love to have something that nails the Sybil attack. But in the end, right, you're choosing between different evils. If you're trying to design a system that is actually perfectly robust to Sybil attacks, meaning it doesn't matter how many Sybils a particular user controls, all the known mechanisms are tremendously complicated. So it really is, there is not the perfect solution, right? You need in the end, for a particular system, see which of these mechanisms is the lesser of the evils for you. And I would submit that if you have a way, in a particular type of environment, you have a way of dealing with Sybil attacks. So in particular in this email system, Sybil attacks were not a big deal, right? Because identities are sort of attached to email addresses. And of course, someone has lots of email addresses they can spam and things like that. That's still the case. But in terms of attacking the system's replication, that wasn't so much an issue. So if you have a reasonable way of controlling membership or limiting the number of identities a user can control, then this becomes a lot more feasible. If you have no handle over this, then it may well be that accountability is not for you or not for this particular system.
I really like the work. I actually like the continuity work. I saw it applied to the Andreas latest paper with net session. And in that context, in that kind of hybrid system, this idea worked great. So I was wondering about, if you can say something about that, if that is if really the solution is going to a hybrid system, like a fully distributed system, like Bitcoin.
If you have some dedicated infrastructure, it's tremendously helpful. I mean, if you look at this net session system by Akamai, it literally avoids many of these problems simply by having a root of trust, by having dedicated infrastructure that is there and you can trust. They still have problems, of course, with Sybil attacks. They still have problems with misbehaving peers. But again, the solutions, we were able to adapt. You sort of refer to this, to adapt some of these techniques to that environment, which, by the way, technically required quite a few changes. Because for one thing, if you expect that all the auditing is being done by a data center, right, then it really becomes important to make that efficient in the aggregate. Whereas if the auditing is done by peers, right, that's not a problem at all. In fact, you want to make the individual auditing efficient. But it does help tremendously. Obviously, if you have some amount of centralized infrastructure, it makes many of these problems tremendously easier.
Regarding the CBO attack, just to be fair, you mentioned that online social networks are a solution. Yes, but they also have disadvantages. I mean, they may be a threat to privacy, and also the behavior of CBOs in social networks is not as initially expected. So,
I agree. I wasn't. In fact, sort of. I think the message was, this is another approach you can take, but it's not perfect. Each of it has its problems. I think how to deal with Sybil attacks is basically very much an unsolved challenge. Yeah.
How do you ensure that a witness is actually correct and provide incentives to become a witness? So in other words, don't you beat yourself in your own tail?
Well, so remember, let me flip up this slide again. If you look at the, there's already, okay. Let me see if I can find it. If you look at these guarantees, you'll notice that in fact, the constraints on the correctness of the witnesses is fairly, I went too far, sorry. Well, never mind. So it turns out that to be able to detect a fault by a node, it's just sufficient that one of its witnesses is correct. Okay? And secondly, even if all witnesses are correct, you can still not accuse a correct node. So that helps tremendously because you don't really have to reason so much about what do we deal about faulty witnesses, and in fact, it's definitely not necessary to audit witnesses. Right? That sort of recursion we don't have to have, and that would be a disaster. Now, it's legitimate to say, you know, how do you incentivize witnesses to do their job at all? I would say that you have to arrange this in such a way that, on the one hand, a node cannot choose its witnesses, obviously, right? That would be bad. That's the one constraint. And the second is you want to choose witnesses among nodes that have an inherent interest in the primary node's correct operation. Right, so if you, so typically speaking, you're interested in your peers, right? The ones that you actually have a peer connection with. Those provide you service, those help you communicate, those help you get things done. So you have a vested interest in those nodes doing their thing correctly. And that's the way you have to set it up. How you do that in practice, of course, again, it depends again tremendously on the particular setup. We applied this kind of technique also for inter-domain routing in the internet, and there the situation is a little bit different. There you want to make the ISP you're peering with your witness, right? Because again, you have a business contract with them, and you have a vested interest in finding out whether they are behaving correctly or not. So my answer is a little bit vague, but it's vague to the extent that you need to look at a particular application, how to set it up. But I think it's doable, right? You just need to make sure that those two constraints, right? A node must not be able to choose its witnesses, and at the same time, the witnesses should have a vested interest in the correct performance of the node.
We should be finishing because we are a little bit late. One last final remark in line with him, and it will be really brief. Pablo was saying also yesterday with the example of BitTorrent that probably we should decentralize in some components and decentralize only the really required ones. So we are really solving very complex problems in a decentralized way that they are quite simple in a centralized one.
Right.
So for example, one of your challenges was controlling membership that is related to all the security, the civil attack, and probably if the future is hybrid system and you have centralized identification, then you can't forget about all these civil attacks and the rest. No?
That's true, although civil attacks are particularly tricky, right? Because there's two problems, right? Centralization would help, but the other thing is there is this trade-off between identification and privacy, right? And if you believe this vision of an internet passport where every person in the world has an internet passport, and somehow the authority that issues those is trusted by everyone in the world, it'll work, right? I'm just questioning whether that is in fact feasible. And this is a problem. It has nothing to do with centralization. Primarily, it's about which organization would you actually trust to certify people's identity, and secondly, how do you protect people's privacy in cases where there's a legitimate need for privacy? So that is I think independently of the centralization versus decentralization question is a tricky issue.
Just a quick question about the time scale which you typically would use to check these logs, because you said you used it to get rid of your secure routing code, but if I have a secure routing code, I can react immediately, for example, to find a better route. Mm-hmm. And in this case, this lookup would fail at first, and only at a later time I can remove this node.
Right. So again, I was assuming here that you have appropriate crypto in place, right, to reduce these kinds of attacks to essentially denial of service attacks. So when you have bad nodes in the system, they will do their thing, right, and you may have to retry certain requests and reroute things to get around them. But of course, you wouldn't want to put up with the poor performance resulting from that in the long run, right? But the nice thing is, if you have this in place, then the period of once such a node has done its first illegal state transition, on the next accounting period, it will be detected, and you flush it from the system.
Thank you.